Kayıda başlayın. Buyur Fatma.
Welcome everyone. So today we have Zehra Demirhan, who is going to speak about p-adic numbers. So Zehra worked on some topics from number theory, and p-adic numbers is a topic that introduces an alternative to the usual field of rational numbers. And I hope that you will find that interesting. Zehra?
Hello and welcome to my presentation on p-adic numbers. Let's start. Here are the contents. Today I would like to mainly talk about p-adic metric on Q and the field of p-adic numbers QP. First, I will begin by giving definitions on p-adic metric on Q. Then I will present you the Ostrowski's theorem and its proof. Secondly, I will give you the definitions of the field of p-adic numbers QP. And secondly, I will present you the completeness property of QP and its proof. Let's start. Let's start by giving the definition of order px for x is an integer. Here p is any prime number, and we define order px to be infinity if x is 0, and we define it to be the greatest power of p such that p to the m divides x, of course when x is not equal to 0. Now we would like to extend this definition to rationals. We do this in a linear way. We consider x as a over v and define order px to be order pa minus order pb. Now let's define our map norm p on rationals. Here, norm p of x equals to 0 if x is 0, and it equals to 1 over p to the power order px if x is not equal to 0. Let's move on. Here is an important definition, which is Archimedean norm definition. An Archimedean norm on a field K is Archimedean if K has characteristic 0. I would like to state that from now on, this field K will be rational numbers in my presentation. And if there exists an integer m such that norm of this m is greater than 1, we say that this norm is an Archimedean norm. Otherwise, it is said to be non-Archimedean. Here are two propositions. One is that the usual absolute value is the Archimedean norm on rational numbers, and the p-adic norm is a non-Archimedean norm on rationals. So these two propositions are easy to check, so I would like to move on with Ostrowski's theorem. But of course, before stating Ostrowski's theorem, I would like to give you two definitions. Let's start by trivial norm definition. Trivial norm is the norm such that norm of 0 is 0, and for any other x, norm of x is 1. And for equivalent norm, we say that two norms are equivalent, let's say norm 1 and norm 2, if a sequence is Cauchy with respect to norm 1, if a norm negative is Cauchy with respect to norm 2. Now, by the knowledge of these two theorems, we can state the Ostrowski's theorem. Now, it says that every non-trivial norm on rationals is equivalent to p-adic norm for some p prime or p equals to infinity. Equivalently, it says that there are only two types of non-trivial distance metrics on rationals, namely the absolute value and the p-adic metric. Now, before proving Ostrowski's theorem, I would like to state a lemma and give a proof of this lemma. Lemma says that let norm 1 and norm 2 be two norms on a field, and if there exists a constant positive real number alpha such that this equality holds for all x in F, then we say that norm 1 and norm 2 are equivalent. In the proof of this lemma, we will use the definition of equivalent norms. So we will try to show that a sequence an is Cauchy with respect to norm 1, if and only if it is also Cauchy with respect to norm 2. But today, I will do the one side of this if and only if statement, since the other side is similar. So let's start by assuming this equality holds, and further assume that an is a Cauchy sequence with respect to norm 1. By the definition of Cauchy sequences, we know that this means the terms of an are getting closer to each other after some point n with respect to norm 1. So we would like to prove a similar result for the norm 2 as well. To do so, let's consider this inequality here. And if we take 1 over alpha power of each side, we are left with this inequality here. Also, I would like to say that we assumed this equality holds at the beginning. So in this equality, we can replace this term by the right-hand side here easily. By doing so, we are left with this inequality, which implies that the terms of an are getting closer to each other with respect to norm 2 also. So the desired result is reached, and the proof of lemma is complete. Now I would like to give the proof of Ostrowski's theorem, but before doing that, let's state Ostrowski's theorem again in a brief way. Every non-trivial norm on rationals is equivalent to p-adic norm for some p prime or p equals to infinity. So the proof of Ostrowski's theorem consists of two cases. Case 1, where the norm is Archimedean, and case 2, where the norm is non-Archimedean. So let's start by where norm is Archimedean. So let A and B two positive integers, and let's write Bn in base A as the following here. Of course, where Ci is between A and 0, and A to the m is less than or equal to B to the m. Now, let's set capital B as maximum of these Ci's. And if we consider the norm of these both sides, and the greatest possible value such that the right-hand side take, we can get this inequality easily. Why is this inequality is true? Let me explain in a detailed way. Here, B is the maximum of the Ci's, and we have m plus 1 terms of the Ci's. And also we are considering the maximum value of norm of A to the m and 1. So here, if norm of A is less than 1, we get 1 as the maximum value. And if the otherwise is true, norm of A to the m is the maximum value here. So this inequality holds. Now let's take 1 over n power of each side. And also let's replace this m by the n logarithm AB. This inequality holds since A to the m less than or equal to B to the m implies it. So we have this inequality, but we can write it in a easier way. Since we know that this term inside approaches to 1 as n goes to infinity, we can replace this whole term by 1, and we are left with this inequality here. Further, remember that at the beginning, we say that our norm is Archimedean. So we can pick an integer being such that norm of this b is greater than 1. Then the above inequality here, this inequality, implies that norm of a is greater than 1, and norm of b is less than or equal to norm of a to the power logarithm ab. Now, if we interchange the roles of a and b in this process, we get the similar inequality here. Further, let's consider logarithm of this both sides for the both equations. Then we recognize that there is a constant ratio between logarithm norm of a and logarithm a, logarithm norm b and logarithm b. So this implies that for all integers a and z greater than 1, we have this equality here, which can also be stated as norm of a equals to usual absolute value of a to the power c. So if you would like to summarize case 1, we can say that we started by a Archimedean norm, and at the end we show that this norm is actually equivalent to the usual absolute value. Now we can extend this result to all of integers, since norm of -1 is 1, and also this extension can be done in rationals as well by setting a as q over d, of course where q and d are non-zero integers. Let's move on to the case 2. Here our norm is non-Archimedean. Therefore, we have for all integer n, the norm of n is greater, lesser, or equal to 1. Also, remember that in the statement of Ostrowski's theorem, it says that these norms are non-trivial. So we should have an n0 such that norm of this n0 is less than 1. Now let's consider the smallest such n0, which is positive. And now we will show that this n0 is actually a prime number and it is unique. We will do this by contradiction. So let's assume to the contrary that n0 is a composite number. Then we have n0 equals to ab for some a and b in integers. Of course, where a comma b is between n0 and 1. Then we can decompose the norm of ab into smaller components, such as norm a and norm b. But recognize that these smaller components are satisfying this inequality. But at the first, we assumed that n0 was the smallest integer. So by minimality of n0, we have that norm of a and norm of b, norm of a or norm of b equal to 1. So hence, we have proven that n0 is a prime number, and from now on, we will call it as p. Now, to prove uniqueness, let's again assume to the contrary that there exists another prime q such that norm of this q is less than 1. And also consider the norm of pn and norm of qm. Now, let's choose n and m sufficiently large that these two terms are less than 1 over 2. And also, we know that the greatest common divisors of these two terms are equal to 1. So we have this equality easily for some a and b integers. And if we take norm of both sides of this equation, and since the norm of 1 is 1 here, we have this equality here. And by using triangle inequality, we get this inequality. Further, we know that norm of p to the n and norm of q to the m are less than 1 over 2. And also for all integers n, this equality holds. So we are left with a contradiction that 1 is less than 1. Hence, if Q is not equal to P, then norm of Q is equal to 1. Now let's consider the prime decomposition of N. Here, if P is not one of these PIs, then since all of the norms of these primes are 1, norm of N will also be 1. But if this P is one of these PIs, then let this P be PI and take norm of both sides. Then we have this equation here. But we know that the norm of P1 until Pk is equal to 1 except norm of Pi. So we have norm of N equals to norm of Pi to the power alpha I in our hand. Also notice that actually this alpha I is the same thing as the order Pin in this decomposition. So let's replace this alpha I by order Pin here. Now for a convenient notation, let this norm Pi be beta and let's write norm N to be beta to the power order Pin. Now I would like to remember you that we are trying to show that the norm that we have started with is actually equivalent to p-adic norm. So we should show by the lemma proven above, norm of N is equivalent to norm P of N to the power alpha. And by the definition that I gave in the beginning, definition of the map, we know that norm P of N equals to this term here. So let's choose a convenient alpha here and let alpha be minus logarithm P to beta. Then this implies that beta equals to P to the power minus alpha. And if we take order Pin of both sides, it can easily see that left-hand side is equal to norm N and the right-hand side equals to norm P of N to the power alpha. So by the lemma we have proved, this implies that these two norms are equivalent. And also I would like to state that this alpha is constant here since this P is fixed and this beta is fixed at the beginning. So to summarize, we have started by an non-Archimedean norm, and we have shown at the end that it was actually equivalent to p-adic norm. So by combining the results of case 1 and case 2, we have proven the Ostrowski theorem. Now, the first part of my presentation is finished. Let's move on to the second part, the field of p-adic numbers. Here's a definition of Cauchy sequences in Q with respect to norm P. Let S be the set of sequences AI of rational numbers such that given a positive epsilon, there exists an N such that this inequality holds if I and I prime are greater than N. Further, we call two Cauchy sequences AI and BI in S equivalent if the difference between their terms with respect to norm P approaches to 0 as I goes to infinity. So by using this definition, we define the set of QP to be the set of equivalence classes of Cauchy sequences. Here are some further definitions about multiplication and addition in QP, and also multiplicative and additive inverses in QP. Let's check the multiplication case. Given two equivalence classes, A and B of Cauchy sequences, we choose any representatives, AI in A and BI in B, and define A multiplied B to be the equivalence class represented by the Cauchy sequence AI-BI. And the followings are defined in a similar manner. So let's move on to the remark. This remark states that the equivalence class of the product is independent of the representatives. So to prove this, let's choose another representative, AI prime in A and BI prime in B. As we know that the p-adic norm is a non-Archimedean norm, we would have this inequality by the triangle inequality of the p-adic norm. So let's consider as I goes to infinity. Then the first term here approaches to this term, and also notice that the second term approaches to 0 after I goes to infinity. So this whole term actually approaches to 0 as I goes to infinity, and the second term similarly approaches to 0. So we have shown that the sequence AI prime BI prime is actually equivalent to sequence AI BI. Now let's move on to the theorem. The set QP of equivalence classes of Cauchy sequences is a complete field with addition, multiplication, and inverses as defined above. So actually, the field properties of set QP is directly inherited from the rational numbers. So I will just give an insight of the distributive property. Here, by using the distributivity of multiplication in rationals, we reach this following result. So the other properties are similar. Now let's move on to the completeness property, which is more interesting. Let Aj be a sequence of equivalence classes, which is Cauchy in QP. Now, from each of these equivalences, we take representative Cauchy sequences of rational numbers, and we call them AJIs. And also we know that these AJIs are Cauchy in QP. Therefore, this inequality is satisfied whenever I and I prime are greater or equal to n for some positive integer n. Now, by this inequality and letting p to the minus j is less than epsilon over 2, we can write this inequality here easily. Whenever I and I prime are greater or equal to nj for some positive nj integer. Now I would like to state that we are trying to prove completeness. So each Cauchy sequence Aj has a limit inside QP. So if you would like to state in a mathematical manner, we can do it as here also. Or equivalently, we can say that the limit of Aj goes to L as j goes to infinity, and this L is in QP. Now let's try to show it. As I prime is greater or equal to nj, we can replace this I prime by nj easily. So remember, here we had this inequality, and now I'm replacing this I prime by nj. And we have the first inequality in our hand here. Now let's consider this term, and let's write this inequality by using triangular inequality again, and consider the second component of the right-hand side here. Here we have a sequence AJI, which is chosen from the equivalence class AJ. So we can say that after some point, let's say m, the terms of this AJI will converge to AJ. So this inequality is satisfied for I is less than or equal to m for some positive integer m. Now, by combining the inequalities 1 and 2 here, this inequality and this inequality, we have that this whole term is less than epsilon. Similarly, we can write this inequality as well here for sufficient large j, of course. So we have proven that as the limit of Aj, we have the equivalence class of the sequence Aj and j, which is also in QP, and therefore each Cauchy sequence Aj has a limit inside QP, and QP is complete. Here are my references. Thank you for your attention. If you have any questions, I would like to answer them.